Hello, my name is Davis, and through this session I'd like to briefly introduce you to software-defined networking. So let's get started. Whenever I hear about any new technology, I ask myself three important questions. Number one, what existed before, or how did the system work until now? Number two, why is SDN any different from what existed? Is this new technology trying to replace what is already existed, or is it trying to build upon the previous system? Number three, what are the use cases or the promises made by this new technology? So let's answer these key questions now. What existed before? So when Robert Kahn and Vint Cerf were building the global infrastructure for communication, they realized that this global system is going to get really complicated as time passes, because the number of users and systems in this network of networks is going to increase. So what they decided was that there needs to be a layered architecture, a layered stack called the TCP/IP or OSI stack in every system that is participating in this global network. Okay, so number two, every node or every system in this network has a particular place in a particular layer of this stack I had mentioned, that is the TCP/IP stack. What I mean to say is, a router essentially operates at layer 3 of the TCP/IP stack. Switch operates at layer 2. That is, a router routes, that is forwards based on layer 3 header of the packet, and a switch switches, that is forward based on layer 2 header of the packet. Number three, a system adheres to the keep it simple principle. So what I mean is, if a router should only be able to route, it shouldn't look at the payload of the packet and recognize, oh, it is a voice packet and it has certain delay and jitter constraints. It shouldn't be able to do this. Rather, it should just forward the packet based on the layer 3 header. So that is what I mean by the keep it simple principle. So number four, every component in this global system or in this network has a control plane, a data plane, and a management plane. So here the management plane is basically how the user interacts with the device. It could be through certain protocols such as SSH or Telnet. And now to explain the control plane and the data plane part, I'll give you an example of OSPF, which is a control plane application for routing. It's a routing protocol essentially. So so that there'll be multiple nodes in your network having the OSPF process running, and these processes would communicate between each other, between the remote node processes, using certain multicast address they would all be listening on. And also they would exchange certain control packets called hello packets for communicating this routing information, right? So what the control plane does is it processes the hello packets, builds the topology table, the database table in case of OSPF, and executes SPF algorithm on it to determine this optimal routes, which is called the data plane, right? So now the data plane, this optimal routes or this routing table, is present at the ASIC of the node or the router or the switch in the network, and the data plane just forwards based on these routing table rules. So the data plane can be viewed as the hands and legs, which is just I route a switch immediately based on this routing table, and the control plane is what builds this table. Okay, so this is how the system used to work or is working at this moment, and let's look at why SDN is any different from what exists right now. So in order to explain SDN, I'd like to give you an analogy of a soccer match. Let's say you're a coach of a soccer team, and your aim, as you know, a soccer game involves getting the ball from your goalpost to the opponent's goalpost, right? So this could be viewed as the source to destination, and the players, right, who's playing the game could be viewed as the nodes in the system, that is the switches or routers. Right now, every player makes their own decision, that is they decide who to pass the ball to somehow get it to the opponent's goalpost, right? And they kick the ball, which is essentially the data plane operation, right? And they make the decision of kicking the ball, which is the control plane operation. Now let's look at the coach who's viewing this match, right? The coach has the holistic view of what's happening. He knows that, okay, if this player had passed the ball, we could have scored a goal much sooner. So here, if the coach had a way to kind of control the minds of the players and to pass certain messages to the players, then we could have ensured success very earlier in the match than later. So this is you could see, so here basically the coach is like a control plane for all the nodes. It's a centralized control plane for all the players or the nodes in the system, and if the communication between the control plane, the centralized control plane, and the players fail, then the players will operate on their own, right? There has to be a fallback mechanism basically, right? So this is exactly how SDN works now. The medium of communication between the centralized control plane and the players or the nodes is basically what we call open flow, and it's essentially, you know, like it's a protocol for communication, that's it. And let's look at these 2 points, right? Each component in the network has a programmable stack. So what I mean by this is, as I mentioned, every node in the network has a TCP IP stack in the kernel space, right? Now, if you could have certain knobs into every layer of the TCP IP stack, and you could programmatically control each layer in the TCP IP stack through a centralized control plane, then that would be wonderful. So because you can pretty much do whatever you wanted. You could encapsulate a layer 4 packet in a layer 2 packet with skipping out on layer 3 encapsulation. So this is what I mean by a programmable stack and a centralized control plane. So now let's look at what are the use cases for this technology. I will focus a bit, I'll spend a little bit of time on WAN optimization in SD-WAN, which is like a functionality of SD-WAN, right? So in WAN optimization, as you know, WAN links are well high bandwidth delay links. So basically, so here we have a client and here you have a server. So the client and server first undergoes a TCP handshake where they discuss how much is the amount of data that I could receive, which is basically the window size, right? So they will communicate before sending the data itself, the window size, and as the client sends enough data as much as the window size, the server has to hack it before the client could send more information again. So imagine a scenario, the client sends so much data that the window size is exhausted, and now the server hacks it. All this time this link is not being utilized because the client is not going to be sending more data until it receives that acknowledgement, right? So what if now one of the intermediate nodes, such as these 2 boxes you see here, could act on behalf of the server? So imagine the client sends data and this box acts on behalf of the server. So that would be pretty awesome, right? So the client can continue sending data and optimally use this link effectively. So this is accomplished using packet rewrites on these intermediate nodes over here, and it is done from it could be through a controller like Ryu or OpenDaylight, on which you write a particular application, you know, to determine, okay, this node needs to rewrite the packet headers to these values to send it to this node. So it all boils down to the application that you write on the controller. So this application, like going back to the analogy that I gave earlier, this application is basically the coach's logic of how the game should be performed, right? So you could write this application in Python, Java, etc. Based on the controller you're using. Also, since the since the controller has a holistic view of the entire network, it provides an additional higher layer of management of the entire network, which is wonderful, right? So number 3 is the network could also become application aware. Now going back to that example where I said a router need not look at the payload to see it's a voice packet, now the router could, because you have a programmable stack and you could essentially perform that operation, and you could give more intelligence to the network. So these are the use cases of SDN. I hope this session was informational, and thank you for watching.